podcasts you love.
From people you trust.
This is Twit.
Bandwidth for Green Tech Today is provided by Cachefly at CACHEFLY.com.
This is Green Tech Today, the Twit Network's Top 25 Green Tech Innovators Series. This episode of Green Tech Today is brought to you by the Eco-Imagination Challenge from GE. GE and its partners are awarding $200 million to ideas that help build the next generation power grid for the 21st century. For more information and to view and comment on ideas, go to ecoimagination.com/challenge. And by MailRoute. Businesses of every size use MailRoute. 1 user to 50,000 users, it doesn't matter. MailRoute will protect you from spam and viruses, simplify your life, and make your email usable again. It's been called a super laser and a star on Earth. But the real implications of the National Ignition Facility in Livermore, California, also known as NIF, are even more exciting. This laser inertial fusion laboratory holds the hopes of mankind for a nearly limitless, clean energy future in its precision-engineered halls of glass, mirror, and light. Still in development, NIF hopes to achieve energy-positive fusion in late 2011 to 2012, making it the first such facility to do so in the world. And in doing so, lead the way into the kind of energy future that so far has only existed in people's dreams. The National Ignition Facility is working on creating sustainable, clean energy for the future. I'm here with Mike Dunn. He's the Program Director for Fusion Energy, also in charge of life here at NIF.
There we go. It's a great job.
It sounds like it would be pretty complicated.
Oh, well, you know, some days yes, some days no. So it's pretty good fun, pretty much most days.
So tell me a little bit about life, laser inertial fusion energy.
So this is a concept that was born about 50 years ago. You know, can we make use of lasers to release the energy that's stored within atoms? And it really goes all the way back to Einstein. Mm-hmm. Can you convert mass into energy? You know, so it's almost the exactly reverse process to that which we use today in nuclear fission reactors. Mm-hmm. You know how those work? You have large uranium atoms, introduce some energy, and those uranium atoms split, equals mc squared, and hey presto, you've got a lot of energy. But of course, you have a lot of byproducts there. You've got radioactive waste, you've got safety issues, and you've got perhaps proliferation issues to do with nuclear weapons. And so for many years, there's been a pursuit of the opposite process. Can we combine 2 small atoms into a slightly larger atom and again release a lot of energy? In our case, isotopes of hydrogen bonding together into helium, releasing energy.
And the process has taken about 50 years since the initiation of the idea of the laser, basically.
That's right. I mean, in May of 1960, actually not far from here in Malibu, California, the laser was born. Ted Mayman introduced the Ruby laser to the world. And actually just a few days after that, a guy here at this lab, at Lawrence Livermore National Lab, called John Knuckles, had the idea of using the ability of a laser to compress energy in time and space, focus it down, and heat matter up to sufficiently high temperatures, the kind of temperatures you get at the center of the sun, enough to bond matter together. So we had that idea. 50 years later, we've now got a facility around us that we hope is big enough and clever enough to actually make that a reality.
Now the laser, what makes it such a good option for creating fusion?
Yeah, so laser light is very different to the light that we see around us now. I mean, laser light is well-behaved light. It's the kind of light you would want in your marching band. You know, all the photons, the individual particles of light, look identical. They all travel in the same direction. They all step in phase with each other. You know, left, right. And so that means you can do a couple of things to the light. You can tell all of those photons to focus down to the same point in space. And you can add as many photons as you like on top of each other into a very small area. And you can also, by the the way in which the laser works, compress the energy in time. So not just in space, but in time. So the way this laser works around us is that we have the laser plugged into the grid, extracts some electricity. That charges up a large capacitor bank, a little bit like the flash in your cameras. When the laser is told to fire, that electricity is released from the capacitors into a flash lamp. Again, just like your camera flash, so you get a burst of light. So that's compressing from minutes down into microseconds. And then the laser itself absorbs that flashlight energy and converts it into the nanosecond timescale. So from minutes through to microseconds to billionths of a second. And if you compress energy in time, you get power.
Right.
Yeah, in our case, we're talking hundreds of terawatts worth of power, more than the entire power that the world produces at any given point in time. But of course, it just lasts for a billionth of a second, a split second. So, but if you can use that split second power, that enormous power focused down to a small spot, incredibly high energies and powers, just use it to spark a reaction, spark a few of those atoms to combine together to create helium, then you get a knock-on process. One creation of helium will introduce the next fusion process, the next and the next, until, if you're clever enough and you've got a facility big enough, you can burn up all your fuel. It's a process that's inherently safe. It gives off no carbon dioxide, of course, and it has no long-lived radioactive waste.
Right.
And it's been known as the holy grail of fusion of energy sources, for decades now. The only problem is it doesn't yet work.
It doesn't quite work. So the goal of NIF, the National Ignition Facility,
Right.
and of LIFE,
is to get to the point where you get more energy out than the laser itself puts in.
okay.
So by maybe a factor of 10 or 20. So you've got a net source of power, a net source of energy. And the project we call LIFE is the means by which we can harness the physics proof of principle that we have here in this facility and convert it into an operational power station.
Okay, so this
Right.
model,
So-
can you explain what's going on
So-
with this model here?
So let me give you a feeling of scale. The NIF facility which we're standing in today is the size of a large football stadium, maybe even a couple of football stadiums.
Okay.
It's the world's largest laser, the most energetic laser. It's actually split into 192 separate laser beams, each of which is about a foot square. And so those laser beams need to compress their energy onto a tiny pellet of fuel. Only needs to be tiny because it releases an enormous amount of energy. And so this is a scale model of the chamber which contains all of that released energy. In reality, this chamber will be 10 meters in diameter rather than about a meter, so this is about a 10th scale.
Okay.
And you can see there's a number of ports around the top and a similar set around the bottom, which are the entrance holes for the laser, grouped into bunches of 4, entering from the top and bottom to hit a centimeter scale oven at the very center of this 10-meter diameter scale chamber. And that little oven heats up to very high temperatures, millions of degrees hot, enough to go from red hot to white hot, all the way up to X-ray hot. So those X-rays can be used to compress the hydrogen atoms together until the point at which, like at the center of the sun, they combine to form helium. And then the sun, of course, goes on to make other components like oxygen and carbon and all the things that we're made of. We don't need to go that far in this system. Making helium is enough, and it releases, if you do it right, if you can repeat this process, gigawatt scale electricity. That's the scale of the largest coal-fired power stations or the large nuclear power stations. But our fuel comes from seawater, and the waste is simply helium gas. So the kind of stuff you blow up a children's balloon with.
Yeah, and helium also, it's running out. So if we can also be a source of helium, that would be...
Helium's in short supply, and a system like this runs at pretty high temperatures on the outside of the chamber. I mean, maybe I should just describe how it works. So it's pretty much like your car engine. Think how your engine works. You inject a bit of fuel. In our case, rather than gasoline, our fuel is hydrogen. A piston then compresses the fuel in your car. In our case, we use the laser as a piston to compress this fuel, not in a linear piston, but actually a spherically imploding ball of fuel, so everything crushes in on itself. And the scale of that piston operation is like squashing a basketball into the size of a pea. So it's a pretty high degree of compression. So a piston compresses the fuel just like in your car. You get ignition. The fuel lights and burns. It's a chemical burn in the case of a car. It's a fusion burn in our case, so it releases millions of times, maybe 10 million times more energy per amount of mass. And then you exhaust, and the process repeats. Inject, compress, boom, exhaust. Just like in your car, if you're sitting at a traffic light, it's maybe idling at 600 or 900 RPM. That's what this system would do. 10 or 15 times per second, just like in your car. But rather than powering a 1-ton vehicle, it powers a city. A gigawatt would power a city the size of San Francisco, which is just down the road, and do so with using minimal fuel, which is available to anybody in the world. It truly is the holy grail, and why people have spent 50 years, and in the case of this facility, billions of dollars to prove that it can actually work.
And as the results of the experiment so far seem to be coming back, is it the proof of concept is proving it more and more viable?
It is. The pursuit of fusion has been a long one. When I was a student, it was still a long way off, and now it's perhaps a year, maybe at most 2 years away from finally being proven. Pretty much on the golden anniversary of the laser. So it's a great time, truly great time to be around in that sense. And so the LIFE project has been born in order to capture the physics that's been proven and converted into an engineering reality. So there's maybe 4 steps that we have to prove in order to get fusion proven to the point at which you could commercialize it. The first is, can you build a laser big enough and with sufficient control that you can ignite fusion? That was completed about a year ago. This facility was dedicated back in 2009. The governor came along, Arnold Schwarzenegger, and cut the ribbon, as it were. We then have to show that we can heat up. Let me show you one of these little ovens. In our case, the oven is about 1 centimeter in scale. This is a full-scale model of the oven that would sit inside that 10-meter chamber. If your eyes are really good, you can maybe see a little red ball at the very center of this gold oven. That little red ball represents a millimeter scale pellet full of hydrogen isotopes.
So the deuterium and the tritium.
Deuterium and tritium, right. So we extract the deuterium from seawater, but 1 part in 7,000 of seawater is deuterium. And the tritium we make in situ, make it actually in the power plant itself. It's a closed loop of fuel. And you can see just schematically the laser beams coming in from the top and the bottom that would heat up this oven. So the second step was, can we actually couple the laser light in? Can we focus it down to a tight enough spot? And can we get it to be absorbed so that the oven heats up? So about a year ago, we did a series of experiments that actually proved that that was possible.
So 2 out of the 4.
2 out of the 4 to that point a year ago. And many people said that it would be simply too hard. The laser light wouldn't couple in enough, and you wouldn't get this system hot enough. Well, it seems that nature's been kind to us for once. First time in 50 years, but, but it's actually been kind to us. So now the third step is, can you get that oven symmetric enough? It's like baking a cake. You don't put a cake when you're baking it on top of the hob because all the heat comes from one direction. You try to put it in the middle of an oven where you get a nice thermal environment. And so we've been trying over the past few months to get that environment to be nice and symmetric so that the capsule sees a hot, uniform oven. That looks like it's gone very well. And so the final step is, can we get that little pellet to be crushed enough to get fusion? Those experiments started just about a month ago in September, end of September, where the full system of this National Ignition Facility came together for the first time. All of the infrastructure that's needed to make these pellets, hold them at very cool temperatures. It sits just above absolute zero, at 17 degrees above absolute zero, because we want the hydrogen to be solid. And of course, all of the laser facility and the diagnostics that measure how hot this gets and how fast the implosion is, all of that came together for the first time at the end of September. And the facility worked a dream, I can tell you. So the confidence in getting this little guy to work is very high.
Very high. So how long now until?
So we believe it will take about a year to tune this engine up. We've got all the engine pieces together. We've shown that they will all operate together. But I guess just like the first time you build a piano or you build a car engine, it's not functioning very efficiently. It's a little bit clunky. And so we know that the codes that we use to design this facility are not precise. They're not good enough to a priori predict what will go on. So we just do some empirical tuning, just see how uniform the pellet is, see how much it implodes, and so refine ourselves. I guess I should just show you, this is the physicist view, this is my view of the pellet.
That's your view.
An engineer's view is somewhat more complex. This is the cryogenic infrastructure that's needed to hold again. You can see the hull ram, that so-called oven at the end of the arm. All of this infrastructure is designed to keep it at 17 degrees above absolute zero, so it's in the solid state, and to keep all of the infrared light that's being radiated by this hot chamber, keep it away from that little cool pellet.
Right.
So this is the engineer's view of how a fusion target looks.
It's nice to be able to see both. How the physicist and how the engineer view the same thing.
And over the course of the next few months, the two will hopefully come together in a way that works. So
yeah. So as you're working to get these working together and toward the next couple of years, you're still working at the stage of just a single laser pulse and a single fusion event.
Absolutely, we are. And so the challenge for life moving forward in terms of converting this to a power station is how do you pick up that single event, the demonstration you can get more energy out than in, and do it repeatedly, do it 10 times a second or 15 times a second. Now, in terms of the physics, there's no issue. One event doesn't know what happened the previous time, so there's no coupling there. It's all about, can you build the technology that operates at that high repetition rate, like an idling car engine. And this is where, of course, the
car won't idle if it just fires once.
Exactly so. You won't get very far down the road. So, and so we need this to operate sustainably over large periods of time, like years, at this high repetition rate. So, of course, since this facility was designed and built in the 80s and 90s, the laser world and the world of the technology of these targets and so forth has come a long way. So we can take advantages of the semiconductor industry that will just transform the way we view this laser. At the moment, the NIF laser is 120 meters long. You've been down the laser bay. It's a large-scale facility the size of a football field. That's using vacuum tube fluorescent lamp technology from back in the 70s and 80s and so forth. Since then, the ability of semiconductors to produce laser lights has evolved remarkably. So just like when you go and buy a television now, you have an LED backlit LCD television, I'm sure you see in the stores. That looks pretty different to the cathode ray tubes we were all used to when we were young.
Absolutely.
The size scale is down by an order of magnitude or more. The same happens with a laser. Rather than 120 meters in length using this flash lamp tube technology, we can be down at 10 meters in length. What that means is that you can build laser factories, put these lasers on the back of a truck and ship them to your power plant. When they go wrong, as of course everything goes wrong every few weeks, I'm sure, you can decouple the laser, send it back to the manufacturer for repair, plug and play your new unit whilst the rest of the plant is operational. So you can remove the uncertainties as to lifetime and reliability of your high threat laser, the thing that's most likely to fail. Decouple that from the plant. So the plant keeps running, keeps churning out that electricity, even though every now and again, somewhere in the plant, one of your laser boxes has failed.
Yeah, so this being the 120 meter long laser,
absolutely.
we can shrink it from here to...
In effect, to about something this scale. So this gives you an overview of the facility we're standing in. So we have the majority of the facility are the laser beams themselves. You can see each of these tubes contains a laser beam about a foot in diameter on a side. You then have to go through a transformation from this 2D array of lasers through a complex series of mirrors to convert into this implosion geometry, this three-dimensional geometry, at the center of which is this 10-meter diameter chamber we saw the model of a moment ago. And at the very center of this enormous facility, that poor little pellet, a millimeter BB-sized pellet containing your fusion fuel. The chamber needs to be 10 meters in scale because the amount of energy given out is such that if it were any smaller, the chamber wouldn't melt. This is a large amount of energy from a poor little pellet.
So we could shrink the laser bays and make the laser bays smaller, but the target chamber itself is going to stay...
That stays about the same. You can shrink the laser bay, you can get rid of all this complex switchyard, these mirror geometries, because you can put your lasers where you need them now, rather than having to relay them along. But fundamentally, your engine, the center of your power station, remains about the same, about 10-meter scale chamber. The very center is a little ball bearing-sized pellet of fuel, and you repetition rate around to get this 10 hertz operation. I mean, semiconductor diodes not only reduce the scale of the facility, They also allow it to operate at 10 times higher efficiency. This is about a 1% efficient laser. Intrinsically, semiconductor systems are very efficient, 10, 12% efficient. And they allow you to cope with those much higher repetition rates.
Right.
This is limited to firing once every few hours, because every time the flash lamps heat up, you've got to let them cool down again, and that takes hours. With a highly efficient semiconductor-based system, you can run these at 10 hertz. You know, you have systems running at kilohertz, megahertz, even using these systems. So, fast operation from a laser is sort of not the point. It's getting the engine itself to operate reliably in this 10 hertz mode, which is what we're working on.
So, as this moves forward, hypothetically, this is all successful. You prove fusion is possible with this technology.
Right.
Do you foresee power stations reaching an economy of scale?
Yeah, so this is the question we've been looking at over the past 2 or 3 years. You know, we're now at the point where we're sufficiently confident ignition will happen that we need to start planning what should happen next. You know, and this takes some time. We can't wait until ignition happens before thinking, yeah, okay, so how do we make use of this?
Now what do we do?
So we've spent the past couple of years talking with the electric power industry, the utilities, the vendors, regulating bodies and so forth, to understand what is the nature of the power grid that will be compatible with this type of facility, and how can we alter the design of this facility to be consistent with what's needed on the marketplace. And that's really driven our design of how to harness the ignition that's been demonstrated here at NIF into a power plant. Made some pretty fundamentally big design choices to make sure we're compatible with the availability criteria, the reliability, and your question of the timeliness. So you look at our current situation here in the United States. You know, because there were a lot of power plants built after the war in the 50s and the 60s, many of those are coming to their retirement age now.
They're reaching the end of their life
They
cycle.
pretty much are. And some are being extended, and if you take even an optimistic view as to the life extension of our coal plants and nuclear plants and so forth, pretty much by 2050, 2060, all of the electricity capacity that's online now will have retired. And then you can make a prediction as to how much power we will need as a nation. It's likely to be what we need now, maybe a little bit more if we have electrification of transport and so forth. So there's a large gap between what we have now and what we will need. Large meaning hundreds of gigawatts of energy requirement. So hundreds of power plants will need to be built over the next few decades. And so there's an opportunity that if we are to replace those power plants with a form of energy that won't further pollute the atmosphere, either in terms of local pollution or in terms of climate change possibilities. And if we're not to replace with a nuclear power plant solution that may have consequences for long-term waste, potentially unacceptable in many areas from a public standpoint, then we have to get moving. You know, we've taken 50 years to get to where we are now. And we can't possibly take another 50 years. So
and even coal and nuclear to build take years to get those plants from regulation, the steps of permitting to actually getting them online.
They do indeed. And
years.
So we've looked hard at how can we make best use of available technology, available materials to minimize the timescale to delivery. Now this may not produce the most highly efficient fusion power station. We could maybe get a factor of 2 better if we really push the technologies, but it gets the delivery perhaps 20 years earlier than if we waited for new materials, more advanced technologies and so forth. So our analysis says that roughly 10 years after ignition, we could have a full scale, in a half gigawatt scale, operating power plant, not at a commercial level at that point, but at the level that would attract the industry and demonstrate to them the viability of operation, the availability of the plant, its operating costs and characteristics, such that you would then foresee in the period leading after that a rollout of commercial stations. You do the maths as to how quickly you could roll these out given realistic constraints on material availability, rate of build and so forth. And something like 25% of the new build power stations by 2050 could be captured by this type of fusion power plants. And that would have a transforming effect on the emissions given out by our country and on the way our electricity grid operates. We're talking hundreds of gigatons worth of CO2 emissions saved. And if you just even put the most pessimistic figures on what that might cost us as a nation. In terms of the lowest possible cost, you're talking hundreds of billions of dollars there in terms of carbon cost to us. So the challenge is out there. We believe we're within a year or so of proving the physics after 50 years of trying. Exciting time.
Yeah.
And reasonably quickly afterwards, by adopting this available technology, available materials philosophy, we think we can have a demonstration plant which goes by the name of LIFE on the ground and demonstrate it to everybody.
So sometime after 2020, we should be looking forward to a demonstration of this as a viable option for reliable power production.
We believe so, yeah. And we believe that's a realistic constraint given the timescales for licensing, for construction, and for proving out the not inconsiderable technologies that need to be integrated together. It's about a 10-year deal after ignition.
And additionally with it, it sounds like there's just benefit after benefit. Are there any downsides that we can see?
So nothing's ever perfect, for sure. I mean, so this is a high technological risk undertaking, that has both pros and cons. I guess it feeds us as a nation in terms of where we would like to go. It talks to a high technology manufacturing base, an industrial base. But of course, it puts some risk of delivery there. The timescales are uncertain because the technology does need to be proven. It doesn't have any carbon emissions, but it does have residual waste which we need to deal with. It's at a level where you would have to store the chamber that surrounds the capsule, that surrounds the pellet, becomes activated because of all the neutrons that are given off. You have to live with that for maybe a few tens of years, 50 years or so, perhaps 100 years, before you get to the point where it's safe to dispose of it in a normal sense.
But that's much less than nuclear waste.
It is. It feels like it's a manageable timescale. Yeah. It's not dissimilar to the decommissioning timescales of large-scale power plants otherwise. And so it's not ideal in that sense. We have to live with that residual decommissioning activity. But it is just 50 to 100 years, not thousands or hundreds of thousands of years. So it feels a manageable proposition.
And then on top of all this, the one thing that as I was reading into what life is looking forward to, was the possibility of fueling these future power stations off of waste.
Yes, indeed. So you can run this system in one of two modes. You can run it in the mode we've talked about, which is a pure fusion mode. Just use the laser to crush hydrogen and get out energy. The energy actually comes out in the form of neutrons that normally would just heat up a blanket to about 1,000 degrees, 800 degrees, and you use that to turn a turbine. Alternatively, rather than using a thermal blanket that just creates heat, you can put in nuclear waste. We could even put in weapons-grade plutonium, of which there's way too much in the world around. Yeah. You could perhaps breed material for subsequent use in a reactor. And the level of burnup could be quite profound. It's in the case of weapons-grade plutonium, you get pretty much complete disposal of the material. From tons, multiple tons entering into the system to milligrams exiting.
Wow.
Now, you do have a byproduct there, of course. Nothing in this world is ideal. You would still then have a high-level waste issue to deal with, as you would with any nuclear reactor when you introduce these heavy metals, high Z metals. So you have a choice to be made there, and we as a society have a choice to make. You're going one or both of these routes. Pure fusion energy production, which has electricity as its core, or the other national missions to burn down our weapons-grade plutonium and reduce by factors of 5 or 10 or so the amount of high-level waste coming out of our nuclear power plants. They're compelling missions. They'll need a lot of licensing, understanding, and approval to get there, and we shouldn't minimize that. That's a very difficult, proposition to develop.
Yeah, there's a long road ahead still.
There's a long road ahead in terms of that so-called hybrid mission, but in terms of a compelling national mission, that certainly exists. And then on the commercial side, producing electricity seems to be a very attractive source. You do the numbers, and it seems cost competitive with other baseload forms of low-carbon energy, whether that be sequestered coal or whether it be fission or whether it be offshore wind. This is as good, if not slightly cheaper in our calculations to date in terms of the overall cost of electricity.
Right, and especially if it becomes something that grows, and there are many plants that end up being built, and maybe not necessarily just here in the United States, but around the world.
There's a real economy of scale here. There's a program underway in Europe that I actually used to run called Hyper that's looking to develop a very similar proposition. The Japanese, the Chinese, and the Russians are all looking into developing this type of system. But here in the US, there is without doubt about a decade's worth of lead. This is where the laser was born. This is taking advantage of what's going on down the road in Silicon Valley in terms of the semiconductor technology. And of course, we have the NIF, of which we're very proud. And we believe this for many years will be the preeminent facility for demonstrating fusion science, and hopefully use it as a stepping stone to producing fusion power stations driven by a laser.
All right. Thank you very much.
Thank you for your time.
Thanks. You heard it here, folks. Maybe it's going to be clean energy in our future. I know, I'm looking forward to it. Soon up, we're going to go on a tour. Stay tuned.
We're partnering with 4 of the biggest venture capital firms in the clean energy space, 3 in the US, 1 in Europe. Again, we think that the combination of GE investment and venture capital investment is going to allow us to increase innovation. It's going to allow us to accelerate new ideas. It puts us shoulder to shoulder with some of the smartest tech investors, and we can use what I would call the industrial clout of GE to bring technologies to this marketplace faster.
GE announced its challenge at a San Francisco event along with its 4 venture capital partners. Emerald Technology Ventures, Foundation Capital, Kleiner Perkins Caulfield and Byers, and Rockport Capital Partners have all joined with GE. Ideas from companies and individuals can be entered through the ecoimagination.com website for the next 10 weeks. So check out ecoimagination.com.
Are you ready? It's time for our tour of the National Ignition Facility. Our guide through this engineering marvel is the NIF Operations Manager, Dr. Bruno VanWonterghem.
All right, so we're now, ready to walk into one of the laser bays, right? So here's where the story starts.
Yeah.
Yes. Mm-hmm. Okay.
Mm-hmm. Okay, so what are we looking at here?
I think we're looking at one of our 2 laser bays. So these are the engine rooms of the facility. Mm-hmm. Here is where the very small and precisely shaped laser pulses are brought up to, very large energies. So we generate about 2 million joules of laser energy in 96 laser beams, each one being about 40 centimeters by 40 centimeters wide.
That's a big laser beam. Most people are probably used to their laser pointers.
Yeah, you're used to the little small laser pointers, and each of these beams by itself is the largest laser in the world. And so we have a collection of 96 beams in this area, and then there's an identical area on the other side of the facility where we have 96 more beams, and all of these beams are combined onto the target in the center of the target chamber.
What factor of amplification occurs here in these laser bays?
So the total amplification is about 15 orders of magnitude. Right? Okay. We send in a pulse that is about 1/1000th of a joule, and we end up with several million joules of laser energy that is then sent on its way to our experimental area.
Neat.
So this system keeps on running, over and over again. There is basically no one that is needed to run and support this system. It runs by itself. It's a very,
you turn on the laser and it'll just go. It'll amplify and amplify until it's ready to leave the chamber or leave the amplifier.
This is really a large photon plant. That's what it looks like. It doesn't look like any laser. Now, if you would climb inside those enclosures, you would basically see, a very nice gallery of optics, because this whole system is filled with large optical systems that are used, either to steer the laser beams around or to amplify the laser energy in the beams. So there's a total of almost 50,000 optical components into this system that is required basically to get all these beams, pointed in the right way and get them all up to the right energy level that we need.
It's really amazing to think about the levels of complexity that must have gone into developing this entire system, and how many different parameters you need to take into account. First, to get the laser the way that you want it, then to get the laser where you want it, how you want it.
Yes, and this was a very exciting process because this is really the first laser that was built by engineers and scientists together. So our previous laser systems that we had looked more like large laser laboratories. We used to be able to access every component and be able to touch every mirror. And this is the first laser where nobody can actually access any of the components.
Right.
Everything is high up in the air, deep inside these structures. And so we had to use an entirely different way of thinking about these systems as handoff systems, and we had to design them almost like a satellite, because you take a
something that you're sending into space that you're not going to be able to access.
We cannot touch it anymore, and that was very hard for us laser scientists to deal with, because you say, I want to touch it, I want to be able to see it.
But it's too big and there's too many parts.
And too complicated, and there are too many parts. So the only way to make a laser on this scale is to engineer it and make everything very compact, close together. That way it's very efficient, and it runs hands-off, so we don't have people that need to touch anything anymore.
There is a little guy in a yellow vest back there.
Yeah, he watches us and stands all the time. He just makes sure nobody touches anything. This is actually what the laser beams would look like if we would stand in the area below us where the beams propagate towards the next area into the facility. You would see an array of 96 beams. This is the real size of the laser beam. It's about 40 by 40 centimeters. As I mentioned, two of these beams probably are the equivalent of the previously largest laser system in the world.
Now you have 96.
Now we have 96 in this bay,
in
actually.
This year, and then another 96.
Yes. So we're still almost a factor of 50 higher in energy than what we ever had before. So we can access a totally new regime with this facility. And that's what we're
something
actually
that
doing
people
right
have
now.
never done before.
Yes, and we're now learning how to deal with that and how to actually use the power of NIF. This is the room where we actually create all the laser pulses before we send them into the large amplifiers.
So this is where it starts?
This is where the laser pulse starts.
Okay.
This is actually the only place in this facility where we have a laser. And the only laser in this facility is actually, very small. It's that little board that you can see right there. Right? The laser itself is a little piece of fiber that is driven by a laser diode. But it allows us to exactly control.
And is this the laser diode? Is this the billionth of a joule power?
Yes, that's
powered
what's
laser
being
pulse?
generated in this room and being sent out into our large amplifiers. I think if we can take a look inside, and we actually can look at the details. So here is where all the precision of the system is implemented, and
wow.
So here is where the computer system can download all the detailed settings.
So you begin the shape of the waveform, the shape of the pulse here with the little tiny pulse that is emanated.
So from the oscillators here that generate the pulse, we then go through fiber optic cables and split the beams into about 48 individual beams. And those can then be controlled in all the equipment that you see over there.
Okay.
And that equipment is in terms
of... So it goes out 48 individual beams from here, then that gets split into the 96.
Yes.
And then the 96 from the two sides.
Come back together as 192 beams onto the target.
Yeah.
Right. So there are 24 beams that go to laser bay 1, and 24 that go to laser bay 2. And then in the laser bays, they get indeed split into 4 individual beam lines to form 96 beams that then get amplified to their full energy level and then concentrated on the target.
Okay.
So the beams start out, as you mentioned, as a very small diameter. The beams, when they get transported, these fibers are about the width of a human hair.
So from the width of a human hair to 40 centimeters by 40 centimeters.
And then when you come to focus, they get back to the width of a human hair once we focus the beams back into the target chamber.
Right. And this here, does this give an idea of what is happening in the oscillation and the,
this actually shows,
the pulses?
This shows, how the pulse shape is being generated. So the red line is typically a power profile of a laser pulse. You see the power starts out mildly, and here is where we start to ablate material from the capsule. And it starts to get hotter and hotter, and then we ramp up the pulse, and then in the end it gets a kick. And that's when the capsule will start to accelerate very quickly and basically collapse on itself and collapse on itself. to form that hot spot. And the way that we actually make that pulse is using a trick where we actually combine a lot of small little laser pulses that are spaced in time, and we can adjust each one of them independently. And so that's how we can translate a particular laser pulse into actual little notes that you can play, and that actually then form the output pulse that is ready to be shipped out.
Right, so you think about it in terms of music, one laser pulse being just one note in the scale, but if you have multiple notes in the scale, suddenly it's a much finer, more complex and interesting sound.
And use that to transmit.
So tell me about the control room. This looks like a NASA. Like
it's
a NASA
actually
control room.
modeled after the NASA a control room. Actually, one of our program leaders is actually former astronaut Jeff Weishoff.
Neat.
On a mission, and helped us really, develop this view on the place where we actually, control the experiments. So this is the only place in the facility where we actually have people during the operations.
So when there's an experiment, a pulse and an ignition experiment, this is where everybody comes.
There's about between 20 and 40 people that are actually seated at these consoles, and they conduct everything from controlling the utilities that supply air and the vacuum systems to the preamplifiers and the systems that inject the laser pulse into the beam. So there we have a console where people actually control the beams in the facility. They align the beams through all the optical components and make sure that it ends up in the target.
Okay. So we're moving into the laser bay. It's a dangerous place, so we have to use our safety materials, hard hat, goggles, safety first. I'm ready to go.
So these are all optical components, lenses, laser glass, mirrors, flash lamps, amplifiers.
How many components altogether? Tens of thousands?
There are about 7,000 what we call line replaceable units, which are complex assemblies, and they may contain another 1,000 parts by themselves. So we have millions and millions of components into this amplifier system that all work together at the time of the shot, just to get all that energy out in that few billionths of a second to get it out, in unison towards the target.
And then you have your laser pulse.
Businesses of every size use MailRoute. 1 user to 50,000 users, it doesn't matter. MailRoute will protect you from spam and viruses, simplify your life, and make your email usable again. MailRoute is a secure, hosted service that filters virus and spam from companies of any size. There's nothing easier for mail filtering than MailRoute. There's no hardware or software to install. You just sign up with MailRoute to start your mail flowing through them, and then they do all the work for you. Visit mailroute.info to sign up. As a TWIT listener, you'll receive a 10% discount for the life of your account. Small business accounts start at $2 per user per month for 10 users, and because of demand from the TWIT Army, MailRoute has added a new service for individual users as well. Visit mailroute.info and sign up with the email filtering service that Tom and Leo use.
Okay, so let's walk inside switchyard 1. So here's where the beams will transition from the laser bay into the target bay. The target bay is located behind the blue wall. And let's see, that's a 6 feet concrete wall that will be used to basically stop all the neutrons that are being generated during an ignition experiments. So they get absorbed and scattered around in the concrete.
And hopefully the amount of radiation that's coming out is not won't make it out past the wall. There's a small amount that actually
makes it into the switchyard. That's why we have additional shielding into the switchyards, and basically it stops completely at that point. So now you see we have a lot of holes into the target bay. So
this door is not as secure as the concrete.
Yeah. But that's why we built this shield door. So these doors actually close and fill in the hole.
Oh, I see.
So these are concrete doors we basically built in place over the last year. So these are one of 48 doors that actually will be used to complete the target bay. And then we have another set of doors that actually then will complete the shield wall around the switch yard.
Safety first. Yeah.
And so in the switch yards, the beams are being transported into these beam tubes. See the beam tubes right there that get the beams from the laser base. And they get split into beams that go up, as you see in those vertical beam tubes. There's another number of beam tubes right there that will take the beams to the level above us, where they can be then sent to the target bay. And the other part of the beams actually are transported down, and they will basically reach the target bay at the lowest level. And so from there on, they go up and to the center of the target chamber. So here we are on the 3rd floor of the target bay. We're actually looking down at the target chamber. See, the target chamber is the blue ball that's right in the center.
Right in the middle there.
Yes. And so the beams, as they come from the switch yards, are pointed towards the center of the target bay. 96 beams again come from the top.
96
and then
from
there's
the bottom.
Another 96 that comes from below and enters the target through the bottom. So to form, the total, symmetric set of 192 beams illuminating the target and the capsule.
Is that the arm that places the target in the center?
That actually is a diagnostic. It's one of the sensors
sensor
that measures the X-ray emission from the gold hole ram.
Okay.
It actually is used as a way to determine the temperature of the inside of that hole ram.
Is that what the X-rays tell you?
Yes. It uses the black body X-ray spectrum to derive what the temperature is of the inside. And so we use this instrument to actually measure that we could achieve 3 million degrees inside that little gold hole ram.
And is that the highest temperature that you've achieved so far?
That is the highest temperature we have achieved in NIF so far, and it is consistent with the requirements that we impose on ourselves. For the design of the little environment of the capsule. So that's an experiment that was conducted late last year, December of 2009. And that was basically a very important step towards the ignition experiment and the tuning campaigns.
Is it going to get any hotter? When you get to the actual ignition moment, is it going to be hotter than 3 million degrees?
Oh, it's going to get a lot hotter. Yeah. Once we get to ignition, we use the radiation that is emitted by the gold capsule to actually ablate the outer layers of the capsule and start to accelerate the material in the capsule such that it basically gets compressed.
Yeah.
And once all the material comes together in the core and stops, all the kinetic energy of that mass that was accelerated to speeds of 1 million miles per hour suddenly gets transformed into heat.
Yeah.
And so you create a little spark in the center of that compression where you see temperatures of 100 million of degrees and pressures of 100 billion atmospheres. And those are the conditions under which the deuterium and the tritium fuel inside the capsule actually ignite. So the two atoms basically come together to form helium, and in the process basically convert a little bit of mass into energy. And that energy escapes in the form of a neutron. So that reaction then propagates and all the fuel burns up into basically a cloud of neutrons that is being emitted, and a little bit of helium basically that stays behind.
So the measurement of the amount of neutrons that you have in the chamber produced by the compression of these atoms together is a measure of the success of your ignition?
And we have several diagnostics that are being used to measure the neutron yield. And you can walk around and show some of those. So we can measure neutron yields in a number of different ways. Some of the detectors are actually located inside the target chamber behind these square boxes. You see that square box, it has a label that says ENTOF, and that's a neutron time of flight. It actually measures the time between the start of the neutron in the reaction and when it arrives at the detector.
At the detector, okay.
And so from that time you can derive, the speed of the neutrons and the energies. So there are several detectors like that we can use to derive the yield or the amount of neutrons that we have generated. We can also determine how dense the matter was after the compression. And other measurements can be made. For example, the instrument that you see right there, that strange looking device, is actually a diagnostic that was developed with the MIT. They basically operate it for us right here. They can measure the spectrum or the distribution of neutron energies from the target. Other ways to measure neutrons are actually by looking at activation of material. Some materials can be transformed into radioactive isotopes when they are irradiated with neutrons. For example, it happens with copper or zirconium.
Okay.
And so we can actually use a little penny with a little piece of material. We let it sit here, and when it sees neutrons, it becomes a little bit radioactive, and then we can go and count the decay of that material and derive from the amount of radioactivity actually how much neutrons were actually generated on the shot.
Okay, so you have multiple ways of determining the neutron impact, or how many there are.
So we have a large set of diagnostics that can really help us determine, the outcome of the experiments, whether that is the temperatures, the X-ray spectra, the amount of neutrons,
how successful
the shape of the implosion. We can actually follow and track the capsule as it implodes, and when it comes together, we can actually measure, its size and how symmetric it was, its density, and all the parameters that are really important for the experimentalists to tell whether they actually achieve the conditions they wanted to demonstrate in that particular test.
Okay. What's this here? This big,
so
this arm
an
is
instrument.
Bigger.
This is a positioner that actually contains an inspection system for the optics. Inside of here is a camera system on a large positioner that we can move inside the target chamber, and it can then look up every individual beamline.
Wow.
It's like a little eye in the center of the target chamber that can look down the laser beam lines, and it can look all the way down into the laser and look at every individual optic along the way. And so we use that, after many shots, to evaluate the condition of the optics and to see if we need to change any optics or whether there's any problems that we need to resolve.
Right. What's the quality of of the laser?
Within a few hours, the system basically can inspect every individual optic inside the system. Over here, we're building actually a very interesting system that will turn NIF not only into the highest energy laser system, but it'll make it the highest power laser system. So all these components are part of a system to take one of the NIF beams and compress it in time by a factor of 1,000. So we can generate a peak power of 10 to the 15th watts, or a petawatt. And
how many watts do the beams currently have when they get here?
It's about the total integrated power of all the beams together at their peak is about 500 a terawatt. 500 times 10 to the 12th watt. So it's almost, several orders of magnitude more.
Okay, so you're going to petawatts.
Yes, in a few individual beam lines. And the purpose of it is such that we can create very high energy X-rays. And those X-rays are actually needed in order to image the imploded core, because the density is so high that normal X-rays or lower energy X-rays do not propagate. So if we would like to take a picture of that core and see what it looks like inside, we need to have very high energy X-rays, and we need to look at a very short time scale, because the whole ignition event is over in a few trillionths of a second.
Yeah.
So we create very bright flashes of very high energy X-rays, and that would allow us to take a little movie of what happens in the final minutes of the implosion event, right before the ignition starts. There's a little baby door.
Little baby door.
Yeah.
Low headroom. Watch your head.
And so you see the entire open space. I mean, it's 10 stories just of steel support structures for all the transport mirrors for the beams.
Right. Wow.
Now, you can see this is 10 stories deep. Right, so the beams get picked off over there from the laser, and then you travel all the way up to the ceiling, the other half, and then they are being reflected towards the target bay. And the other side of the beams are traveling down, and then all the way to the basement of the switchyard, we have a set of mirrors that send them and across into the target bay. So it's very stable. I mean, big steel beams to keep the mirror stable, along with, I mean, very precise temperature control in the area. It just keeps all these beams pointed for, I mean, several hours on end, from the time that our computer system takes it up, picks it and puts it on the target. That we have time to basically complete our shot activities and make sure that the beams are still where we think they are.
Do you have seismic controls in here for in the possibility of earthquakes, or?
Yeah, the seismic controls are really implemented by the amount of concrete and steel. I mean, the foundations are anywhere between 3 feet and 10 feet, and the building is designed to handle earthquakes that would be several times the Loma Prieta earthquake, for example, without seeing any effect. So during an earthquake, this is the place to be.
Yeah, I want to make sure I can come back on that day.
Yeah.
Because you don't, for any kind of an earthquake, you don't want the optics to move at all.
No,
everything
we've
has
designed
to
it with
stay
very
completely
stringent
stable.
criteria that we basically can recover, even in some cases without any realignment of the equipment, right, so that everything just stays in place. And then, if a real large earthquake would happen, then we may have to realign some components there. But we have designed it so that we can handle and withstand a 1,000-year earthquake, which is a very stringent criteria.
That's very stringent. Not everybody does that.
So even inside these enclosures, the beams propagate through an argon atmosphere, because the beams are so intense that they cannot propagate through normal air, basically without losing some of their energy, or they would interact with the air molecules. So we keep an argon atmosphere as long as the laser propagates at their peak intensities towards the target chamber.
Does argon fill the target chamber as well?
The target chamber itself is completely evacuated.
Evacuated, okay.
Right? Because
So
the
there's
laser
nothing
beams
for the-
would basically completely ionize every gas or molecule that it would encounter on its way.
Okay.
It would distort the amount of energy that it can develop to the target. So the target chamber itself is a large 10 meter diameter, vacuum sphere. And it's almost used the same way that like a torpedo is loaded. The little port is opened on the back, and a diagnostic can basically be inserted. You can
Through the end.
close the load lock, pump it down, and then it gets transported and moved inside the target chamber. And so these are really our workhorses, because they tell us everything what's going on with the implosions.
Yeah.
For example, our X-ray cameras that take the little snapshots of the capsule that's imploding are all using this type of equipment.
Okay.
You can see from the side, right, the laser beams travel through this tube. There's a mirror located into that structure that sends the
Bounces
beams
the
up.
beam up.
And then the bottom 4 beams continue to propagate. And there is a mirror located all the way at the end
That
to
bounces
send
it
the beam down.
Okay. Yep.
So in that entire I mean, volume and structure is filled with argon in order to keep the beams together as they propagate at these high intensity levels when they leave the laser. Okay.
That's it for this episode of Green Tech Today. I'm Dr. Kiki, and I'm done green hunting for this week. Find me someplace new and exciting next time.
That's it for this episode of Green Tech Today. Subscribe at twit.tv/GTT and never miss a show. If you have a question or a comment, email us at greentechtoday@twit.tv. Or you can leave a voicemail at 415-GT-TODAY.